Have you ever thought that these four topics that are written on the screen, combinatorics, linear algebra, time series, and Markov chain, they are connected together? That's a question that I pondered upon, and I came upon a problem that can show you the relationships. Let's get started. So we have this problem here that tells you that you have to count. So it's a counting problem. So we're doing a counting problem, and we'll connect all these three topics, these varied topics together. So you have a counting problem. The counting problem says that you have to count a number of 8-digit positive integers such that the positive difference between two consecutive digits, any two consecutive digits, is greater than or equal to 7. So let's take some examples. Let's say you start with 1. So the difference should be at least 7. So this is not correct, okay? So this is not correct because after 1 you cannot have 7 because the difference is 6. So let's take an example. Let's start with 1. So with 1, so once you start with 1, then since the next difference should be at least 7, the difference with the next digit should be at least 7. So you should have either 8 or 9. So let's put 8. Now once you have 8, the next difference should be at least 7. So it can be either 0 or 1, right? So let's put it 0. Now once you have 0, then the next will be at least 7, 8, or 9, right? Like either one of them. The difference, and the difference will be at least 7. Hence, the next next digit should be 7, 8, or 9. So let's say you put 9. Now once you put 9, you can have the maximum like difference is possibly is 9, because you can have 2 that is the difference is 7, 1 that is the difference is 8, and 0 that is the difference is 9. So let's put it 2. So if you put 2, now observe that you can have only one, 9, only one possibility, 9, right? Again 9. So let's put 1. And if you put 1, next possibility can be either 0, 1, or 2, right? If you put 1, the next possibility again after 1 is 8 or 9. So let's put 8. So this is the valid number. Also, the difference is 7 here, is 8 here, is 9 here, is 7 here, is 7 here, is 8 here, is 7 here. So all of them are at least greater than or equal to 7, at least 7. So here it's 6, so it doesn't follow the rule, but the others are 7. So if one of them is false, then it's not such a number that we are looking for. So we have to find these numbers like this, where the consecutive difference should be at least 7 and it should be 8 digit. Now, as you can understand that there's a simple algorithm that's happening behind. What simple algorithm? If you place a number, there's a set of possibilities. You're just picking among one of them, and then again moving on to the next. There's a set of possibilities. You're picking any one of them, and then moving towards the next, right? So observe that you can never have 3, 4, and 5. So these are never possible. Why? Because there is no number, there is at least no digit from 0 to 9. There is at least 7 distance for any one of them. For them, it's the first 7 distance comes up for 3 is at 10. Okay. And if you take the negative side, it comes up at less than a positive number. So the positive difference for 4 is 11 and 12. So these are not integers from 0 to 9. So therefore, the difference, they will never occur in this sequence of digits that we are looking forward to find. So therefore, these are not there, right? So therefore, there is some connection inherently with this movement of one digit from another. Let's try it out. So from 0, what you have the following possibilities. You can go from 0. If one digit is 0, the next digit can be 7, 8, or 9, right? Let's take a different color. For 1, you can have 1 can go to either 8 or 9, right? What about 2? 2 can go to only 9, right? After 2, the next number should be 9, can be 9, should be 9. So let's stick now for 7. From 7, you can only go to 0. From 8, you can only go to 0 or 1, not 2, because the difference becomes 6. Let's take a different number. 0 and 1, not 2. And from 9, you can go to all of them. From 9, you can go to all of them. Now you can see it's a bit, it's a bit suffocating to see all these arrows and stuff. So we can observe that we can arrange this geometry, this movement in the following picture that you can see on the right hand side. So observe that if you have two of like arrows like this from one another, we are replacing it by arrow like this. If it's just one directional, we are replacing it by unidirectional arrow. Okay, so let's explore this. So from 0, you can only go to 7. You can see the arrow here, this one. You can go to 8, you can go to 9. From 1, you can go to only 9 and 8. From 2, you can only go to 9, right? And from 7, you can go to 0. That's it. And from 8, you can go to 0 and 1. And from 9, you can only go to 2, right? So therefore, this picture is equivalent to this picture. And it's much more clean. You can observe this. It's much more clean. So this tells you how the whole algorithm is happening. So now what you do, you start with any number and you follow this one by one, okay, and see the possibilities. Now that's a hard work. So there's a movement, there's a strategy, there's an algorithm given that how the whole thing is happening. So you can let a computer do it, but there is a beautiful another way to do it. Okay, so you are telling you're inputting the algorithm. The algorithm is that this is how the number should move. If somewhere there is 0, it can have the following possibilities. So you take all the possibilities out there, right? And you find the total number of combinations, you count the number of combinations. Okay, now how to do that? Do you have to draw a tree like this? Like let's say it starts with 1 and then the possibilities are 8 and 9, right? And then from 8 and 9, the possibilities are 1 and 0, 0 and 1. From 9, the possibilities 2. From 0, you can have only possibilities 7, 8, and 9. And from 1, the possibilities are 8 and 9. So you can see it's a long thing. For example, this 1807 gives a good, a valid, 4-digit number. But essentially it's compute the number of leaves, number of end elements of the tree, number of paths in the tree, just like you do the, you do permutation combination problems. You compute the tree and find the number of such paths. But this is a hard work. A hard work means it's not easy to do it. You can make a computer do it. So how to do it by hand? How to do it? How to arrange this problem in a way that you can do it using very beautiful mathematics? And that's where linear algebra comes in. So we will do a simple, small trick. What we'll do, we'll define these quantities. So we'll define in, which is the number of n-digit integers, positive integers, that starts with I. Okay, and you can see 0n is the number of n digits positive integers that starts with I, or that we can say non-negative integers. Okay, no, positive integers that starts with I. Great. Now observe that 0n is nothing but an n-digit number that starts with 0, and there are remaining n minus 1 digits left. The remaining n minus 1 digits left. So now, therefore, after 0, you have possibilities of 7, 8, and 9. So let's understand this very carefully, that after 0, there's possibility of 7, 8, and 9. So here it can be 7, here it can be 8, and here it can be 9. So these are the three possibilities that you can have after 0. Now observe the number of digits, number of n-digit integers that starts with 0 is equivalent to the number of, now if you, now you're counting the number of such integers, right? So essentially it's counting the number of such integers whose first two digits are 07, 08, and 09, right? Therefore, you can also say the number of n-digit integers that starts with 0, essentially the number of n minus 1 digits integers that starts with 7, and n minus 1 digit integers that start with 8, and n minus 1 digit integers that start with 9, right? So since 0 has three possibilities, you are dividing into three possible cases by addition principle of combinatorics, and you can see these are the only three disjoint possible cases, and therefore it's equivalent to saying that number of n-digit integers that start with 0 is equal to the number of n minus 1 digit integers that start with 7 plus the number of n minus 1 digit integers that start with 8, and number plus number of n minus 1 digit integers that start with 9. So we have, because one place got reduced, this place got reduced, so you can easily, you know, you can easily remove this part, the 0 part, because for counting this is not important. So you can see it reduced down to n minus 1 digit integers. Whatever you put, number of different possibilities, that gives total number of count. So therefore, wherever the arrow is going, accordingly it will behave. You can find this relationship. This is called a recurrence relationship. So 0n is equal to 7n minus 1 plus 8n minus 1 plus 9n minus 1. Now 1 is equal to 8n minus 1 and 9n minus 1, just following this algorithm. So if you write down this algorithm, this will turn out to be this set of following 6 equations. Now, there is one beautiful aspect that is yet to be revealed. And the aspect is, you can represent this as a matrix. How? Imagine this is a set of linear equations, right? So now observe, you can write this as, if you take a vector, Vn is equal to 0n, 1n, 2n, 7n, 8n, and 9n. And a Vn minus 1 will be corresponding 0n minus 1, 1n minus 1, 2n minus 1, 7n minus 1, 8n minus 1, 9n minus 1. Observe that you can write this entire equation, set of equations, linear equations in the form of this matrix. And that turns out to be this matrix. And what we have to find, nothing but 1/8, the number of 8-digit integers that starts with like 8-digit integers, so it should not start with 0. So we want that 1/8 plus 2/8 plus 7/8 plus 8/8 plus 9/8, right? So therefore it's a part of V8, right? So therefore we have to find V8. Now observe that V8 is nothing but, observe that V2 is nothing but A into V1. So therefore V3 will be is equal to A into V2, which is nothing but A square times V1, because we replace V2 by A2. So therefore V8 will be nothing but A to the power 7 times V1, right? It will be nothing but A to the power 7 times V1. And once we find V8, we can add up this 1, 2, 8, 1, 8, 2, 8, 7, 8, 8, 8, and 9, 8 to find out the required result. So V8 is equal to A7 into V1. Now, what is V1? V1 is the number of, let's say 1, 1. What is 1, 1? 1, 1 is the number of one-digit integers, positive integers that starts with 1 with the consecutive with the condition, but there's only one digit, so that consecutive relationship doesn't exist, right? This doesn't hold. So there's like I1 is always 1, right? Because there is no consecutive relationship. There's only one number which starts with that number, and hence that is the number. So I1 is that number. So V1 is 1, 1, 1. And therefore V8 is nothing but A to the power 7 times this 1, 1, 1, 1, 1, which is nothing but the sum of the rows, right? Now if you sum of the individual rows, so any matrix, let's say A, B, C, D, if you multiply 1, 1, 1, 1, 1, it will be the first element will be A plus B, and second element is B, C plus D. So this is nothing but the sum of the elements of the rows, first row. This is nothing but the sum of the elements of the second row. And there's 6 kind of rows. So therefore, you get the corresponding equation as I have written over here. The vector will be sum of first row, sum of second row of A to the power 7, okay? And last will be sum of sixth row, which is nothing but 0, 8, 1, 8, 2, 8, 7, 8, 8, 8, 9, 8. Hope it's clear. So therefore, see, observe how, therefore it boiled down to compute A to the power 7, and it can be easily doable, right? By a computer. You can teach a computer to do it, and this is computed by one of my students, Sai Kamath, and we got this matrix, and therefore what we are required to find, this is nothing but if you sum of the elements here of the row, we will get the numbers. This sum will be nothing but 1 8 2 8 7 8 8 8 9 8 and 0 8, and if you sum it up, the answer will be 1 2 3 3. Right? It's beautiful, right? How we can transform a counting problem into a linear algebra problem. We transform this counting problem into an algorithm. That algorithm is transformed into a set of equations, and the set of equations transformed into the matrix, and therefore finding the solution turns out to be nothing but just basic equivalent to finding the a to the power 7 matrix with the sum of the a to the power elements, row elements of the a to the power 7 matrix. Beautiful, right? But there's more to it. What more? This is a very important graph, and this has caused history in the field of statistics, and that is called Markov chain. Ah, now, imagine this experiment, okay? What you're doing. Imagine you start randomly. Imagine you start randomly with any one of these digits. The first place in any one of these 1, 2, 7, 8, 9, any random. Therefore, the next, whatever you put, is can be described by a probability distribution. How? This will reduce down to something interesting. This equation will reduce down to something, this matrix. And that is called a transition matrix. So observe that this, you can rephrase this as now 0 can go to 7. So 0 has possibilities to go to three possible positions, 0, 7, 8, and 9. It can go equally, likely. So it's 1 by 3, 1 by 3. So now we need the bigger one. So 0 can go to 7, 8, and 9 as 1 by 3. There are three possibilities, right? 1 can go to not 7 but 8 and 9, with the two possibles, so half, right? And 0, so 2 can go to just 1 with probability 1. So 1 will go to 2 will go to 9 with probability 1, and 9 will go to 2 with probability 1. And 7 will go to 0 again with probability. Sorry, I have done a mistake. So 9 has more possibilities. I have done a mistake. So 0 will go to 7, 7 will go to 0 with probability 1, 8 will go to 0 with, so 8 can go to 0 and 1, so with probability half, and 9 will go to 0, 1, and 2 with probability 1/3, 1/3, and 1/3. So therefore, you can imagine that every single time, so first step, you select randomly out of 0 to 0, 1, 2, 7, 8, 9, and then the next one is represented by this probability distribution, right? Whatever is the, let's say you get 7 here, so then you toss, or you find, like, you simulate one of the, this distribution with respect to 7. That is, 7 can go to only 0, so therefore next one will be surely 0. Now once you get 0, they have three possibilities. Now you randomly select one. Essentially it's like counting only. You're not counting the entire thing, but you are thinking in terms of probability distribution. So the statement I usually make, that classical probability is always equivalent to counting. Okay, so now you can see it's classical probability. If 7 had a more probability of going to, like, let's say 0 has a more probability of going to 7 than 8 or 9, then this wouldn't have been a combinatorics problem. So classical probability, one reason you can connect this to each other is classical probability is equivalent to combinatorics counting, because it's equally likely and you can mathematically prove it. And therefore, this matrix can be represented by this matrix only. Observe, it will be nothing but 1 by 3, 1 by 3, 1 by 3. Three possibilities, 1 by 2, 1 here, 1 by 1. So 1 by 2, 1 by 3, 1 by 3. So this is now transition matrix now, where you can go from 0, 1, 2, 7, 8, 9 to 0, 1, 2, 7, 8, 9. And now using this, you can find out the also the relationship and what it will be there, what's the probability of that, and you can multiply by that with the total number. But the basic idea is that every such classical probability problem is equivalent to combinatorics, and here a digit, a sequence of digits is nothing but a time series model. So a combinator, the why I am calling Markov chain related to time series, because understand time series is based on time. So this experiment I have told you, so first randomly select one of the numbers from 0 to 9, and then you select according to this process this I have told you. So it's happening a long time, you're selecting one by one, so it's a time series data. And Markov chain is the first non-IID model of the time series data. Okay, non-IID model, so therefore it's very exciting. It's a non-IID model of the time series data, so it can be used to understand relationship that is happening, that is time dependent, and that's the beauty of it. Okay, and that's why it's so elegant. So there's IID, we assume in probability and statistics that the sample is IID, but in certain cases the sample is not IID, as it depends on time. So Markov chain is one of the most beautiful and elegant and simple model to address this issue, where there is 1 degree relationship. So like local 1 degree relationship. So that's a beautiful idea. Okay, I hope you enjoyed it, guys. I hope you liked it. If you liked it, do share with your friends and people who will enjoy this discussion. Share your ideas in the comments, and thank you for attending, thank you for watching me, thank you for listening to this till the end. So have a great day ahead. Stay tuned and stay blessed. Bye bye.